The second type of reaction that we're going to study is called a hydrogenation reaction. It's also a form of an addition reaction of alkenes, and the conditions required for this particular reaction are: you need hydrogen, you need H2 molecules. So you need hydrogen, and a nickel catalyst is required. So nickel as a catalyst is used. If you don't have nickel, then platinum or palladium are also used as catalyst in this particular reaction. So those are the symbols of platinum and palladium. They are also other options of catalyst that can be used in this particular reaction. And the last thing is that the temperature required for this particular reaction is around 200 degree centigrade. Now what happens in this reaction is that you have an alkene. You take an alkene. Let's say we're going to start off with the simplest alkene. I'm going to give you an example of ethene, which has two carbon atoms having double bonds. So that is an ethene molecule. You react it with the hydrogen in the above mentioned conditions. You have a nickel catalyst and the temperature is 200 degrees centigrade. What happens is that, again, what's going to happen is that this particular double bond, you're going to draw this ethene molecule without this double bond. Instead of this double bond, you're going to have a single bond. So redraw the molecule, don't change anything else except that instead of the double bond, you now have a single bond. So let me highlight this. It's going to be, I'm talking about this single bond. So I had this double bond initially, and now I have this single bond. I haven't touched the other part of the molecule. I've drawn it exactly as they were before. And now if you look very carefully, these two carbon atoms now are making 3 bonds each. They should be making 4 bonds. So this carbon atom is going to make a 4th bond with a hydrogen atom that is coming from this H2 molecule over here. Similarly, this carbon atom is going to make another bond with hydrogen, and that hydrogen atom is also coming from the hydrogen molecule that I've circled over here. So in this particular reaction, alkenes, and you take an alkene and the end product is going to be an alkane. So the importance of this reaction is that an unsaturated hydrocarbon is going to be converted into a saturated hydrocarbon. By the term unsaturated, I mean any hydrocarbon that contains carbon, double bond carbon, is going to be converted into a saturated hydrocarbon, in which it is all the carbon atoms are making single bonds. So this is the very important application for this reaction, and this application is it's generally evident in the formation or used. Its main usefulness or uses for this particular reaction are that it's used in the formation of margarine. Now in the formation of margarine, what happens is that unsaturated edible oil is converted into saturated substances. So that is the importance of this reaction. And why does the industry convert unsaturated edible oils into saturated edible oils? Is that it helps in increasing the melting and boiling points. The melting and boiling points. And how are the melting and boiling points increased by performing this reaction? They increase because if you go back and have a look at the reaction, what is actually happening is that this ethene has a smaller MR. It's a smaller molecule. So it's a smaller molecule. You can see that the formula for this molecule is C2 and H4, and that molecule is converted to a larger molecule whose MR is C2H6. So whenever and this applies to all hydrocarbons, that larger molecules are going to have higher melting and boiling points because they are larger molecules. So this is how a smaller molecule, in this case ethene, which has a low melting and boiling point, is converted to a larger molecule having a higher or just a slightly higher melting and boiling point. So you might have noticed with margarine is that if you take the common butter that you get from the stores, that butter has a lower melting and boiling point, but once it is hydrogenated, margarines don't melt that easily. So they tend to have a larger melting and boiling point. So that's the importance of this reaction. And now I'm going to do a few more examples of this reaction. Let's try and do a few more examples for this reaction. I'm going to take 2-methylpropene. So if I have 2-methylpropene, that means propene means that they are a total of 3 carbon atoms, and propene means that there's going to be a double bond. It's an alkene, and 2-methyl means there's a branch of methyl on the second carbon atom, so there's going to be 1 carbon atom. Meth means 1 carbon atom, and I'm going to complete the bonds by drawing all the hydrogen atoms. So this carbon atom is going to be making 2 more bonds, and the carbon in the center, that has all its bonds complete, and I'm going to react it with hydrogen for hydrogenation. The temperature would be 200 degrees centigrade, and the conditions would be a nickel catalyst. So I'm going to redraw this molecule, and I'm going to focus on this double bond. I'm going to redraw this molecule, keep everything exactly the same, except that instead of the double bond, I'm going to have a single bond, and I'm going to draw the entire molecule as it is, no change done to any part. So there are 3 hydrogens over here, and there are 3 hydrogens on this side. Similarly, there are 2 hydrogen atoms over here, and if you look carefully, I've drawn the entire molecule as it is, except for this single bond. I've changed this. Instead of drawing a double bond, I've drawn a single bond. And now what I'm going to do is I'm going to see which carbon atom, this carbon atom over here, is now no longer making 4 bonds, it's making 3 bonds once the double bond is not present. So I need to complete its bond, so there should be a hydrogen atom attached over here. One of the hydrogen atoms from this molecule over here is going to get added up to over there. Similarly, this carbon atom is not making 4 bonds, so 1 hydrogen atom has to be added over here. So you have 2 hydrogen atoms being added to a molecule, and again the same thing happens. An alkene, which is an unsaturated hydrocarbon, is converted to an alkane. So that's an example of this reaction, and we're going to do a few more examples later on. The third type of addition reaction is called a hydration reaction. It's a reaction of alkenes with H2O. So this reaction is a reaction of alkenes with H2O, and the conditions for this reaction are that it's carried out at 300 degrees Celsius and at an atmosphere at a pressure of 60 to 70 atmosphere pressure. And remember that since you're doing this reaction at a very high temperature, so you wouldn't be reacting it with water. You would be reacting it with steam instead. So this is a reaction of an alkene with steam, and I'll give you an equation for this reaction, and I'm going to start off with the simplest alkene. I am going to start off with ethene. Now this is an ethene molecule. It's going to follow the same exact mechanism as all the other addition reactions that we have studied so far. So we're going to have a water molecule which is going to react with ethene, and when it reacts with ethene, so when it's going to react with ethene, again you're going to draw this ethene molecule exactly the way it is, except for the fact that instead of drawing a double bond, you're going to draw a single bond. So you're going to get rid of this double bond, and in its place you're going to have a single bond. So that's what you're going to do. And when you replace a double bond with a single bond, these two carbon atoms are now no longer making 4 bonds, they're making 3 bonds. So they need to make one more bond each. So this carbon atom is going to bond with hydrogen, and the other carbon atom is going to bond with an OH group. So what you're going to notice in this particular reaction is that your water molecule is going to split up into 2 parts. One part would have hydrogen and the other part is going to have OH. So it's going to split up into 2 separate groups, and one group is going to get attached to one of the carbon atoms, and the other OH group is going to get attached to the other carbon atom. So this is how this reaction is going to be carried out. It's exactly the same as we've studied all the other previous reactions. So an H and an OH group get added to both the carbon atoms. So what the significance of this reaction is that an alkene is going to be converted into an alcohol. Due to the presence of an OH group, it would be an alcohol. In this particular case, you have ethene, which is converted to ethanol. And I'm going to do a few more examples. Let's take a more complicated molecule. I have let's start with 2-methyl-butanene. And I'm going to react it with steam. So 2-methyl-butanene contains 4 carbon atoms, and it has a double bond. Due to this one butanene, it's going to have a double bond at the very first carbon atom, and there's going to be a CH3 branch on the second carbon atom, and I'm going to draw all the other hydrogen atoms as it is to complete the bonds of carbon. This is going to make 2 more bonds with hydrogen, and this is going to make 2 more bonds with hydrogen, and the last carbon atom is going to make 3 more bonds to complete its 4 bonds. So that's 2-methyl-butanene, and if I react it with water, then my product is going to be, you redraw this entire molecule, but instead of this double bond, you're going to have a single bond. So I'm going to redraw the entire molecule as it is, except for the fact that instead of the double bond, I'm going to draw a single bond. So this had 3 hydrogen atoms, this had 2 hydrogen atoms, this carbon had a branch and it had 3 hydrogen atoms, and this particular carbon atom had 2 hydrogen atoms. Now if you look carefully, again these 2 carbon atoms are now no longer making 4 bonds, but they're making 3 bonds. So something else must be added to it. So hydrogen is going to be added to one carbon atom, and OH is going to be added to the other carbon atom. Now this is a slightly different case because all the rest is similar to all the other addition reaction, except for one tiny difference. we had OH attached to one carbon atom and H attached to the other carbon atom to complete their bonds. But the position of the OH and the H group could have been reversed. You could have had H attached to this particular carbon atom and OH attached to this carbon atom. You can reverse the position. So both cases are true, but there's a general rule that applies to A levels. In O levels, you can get away with this. You can attach OH or H on either one of the carbon atoms. It is not they're not going to penalize marks for that. But there's a general rule that applies, and that rule is that the hydrogen atom is going to get attached is going to be attached to the carbon atom which has more hydrogen atoms, which has more hydrogen atoms. So although both products are possible, instead of having H over here, you can have OH over here and H on the other carbon atom. But the general rule is the major product that's going to be formed is going to be the one that I've drawn. The hydrogen atom is going to be attached to the carbon atom which is already attached to more hydrogen atoms. So this carbon atom over here is attached to two hydrogen atoms, whereas this carbon atom over here is not attached to any hydrogen atom. So the hydrogen atom that we're going to attach is going to get attached to this particular carbon atom. And I can do a few more examples explaining this concept. We can have another molecule, another example. Let's take a simpler example of propene. So propene has a double bond and it has these hydrogen atoms. I'm completing all the hydrogen atoms. So this is a molecule of propene, and I'm going to react it with water, H2O. So I'm going to react it with water, H2O, and if I redraw this molecule, I'm going to again get rid of this double bond and replace it with a single bond and keep the rest of the molecule as it is. So instead of this double bond, I'm going to draw a single bond. The rest of the molecule is exactly the way it was before. And now I'm completing the diagram. Now these two carbon atoms over here, their bonds are no longer complete. So the water molecule is going to split up, and H is going to get attached to one carbon atom and OH is going to get attached to the other carbon atom. Now which carbon atom would H get attached to? H would get attached to this particular carbon atom because it's already bonded to, if you can look, it's already bonded to two hydrogen atom, whereas this carbon atom over here is only bonded to one hydrogen atom. So hydrogen atom is going to get attached to the carbon atom which is already bonded to more hydrogen atom, and this carbon atom would be attached to the OH group. Although if you're in O levels, it won't matter, you can attach H over here and OH on the other side, but for distinction purposes, if you're aiming for a distinction, then you would have to draw the most correct diagram, and you have to give the most correct answer to obtain a distinction.